Okay, welcome to 10.04, where we're going to be talking about the second derivative test today. So this is going to be similar to the first derivative test in a lot of ways, but the second derivative test is used to find concavity of our graph. So we're just going to take a quick minute to review what concavity means. So remember that if something is concave up, it's going to have this kind of shape right here. It may have a minimum, so I'm just going to make some notes to myself. It may have a minimum, and we know that f prime changes, so the slope actually changes from, let's see, it starts off as a negative slope, gets to 0, and then turns into a positive slope. So we'll just say negative to positive, right? Now, there's something called f double prime, which is the second derivative, and this is actually going to help us determine our concavity. So f double prime is actually going to tell us our concavity, which is actually the change in the slope. So how is the slope changing? So it starts off as very negative, let's say like -2 or something like that. It gets less negative, like -1. We know that this is definitely flatter, but still negative, to 0, to maybe like a +1 to like a 2 or 3 here. So we change from very negative to very positive. So the slope is actually increasing the entire time, right? So think about if you were to compare all the slopes, that would be increasing. So f double prime is going to be positive that entire time. So this is like the change in slope. Okay, and this is going to tell us our concavity later on. All right, so similarly, concave down is when we might see a maximum value. And we know that f prime, the slope itself, goes from, let's see, it goes from increasing to decreasing. So f prime changes. The slope is always changing. And it changes from a positive to a negative. All right, that's what we had from the first derivative test. Now the second derivative test, once again, tells us our concavity. So how is the slope changing? Well, it's very negative, let's say like -2 or -3. Or sorry, very positive, let's say +2 or +3, right? And then it gets less positive, right? Maybe like a +1, flatter, to 0. To then to like a negative, let's say like a -1 or something like that. And then very negative down here, -5, negative whatever. So it's going from very positive to very negative. So the slope itself is changing the entire time. It's going to be negative. So that kind of tells us that basically f double prime is how the slope is changing. So it's going to be decreasing. Okay, so that's going to be our change in slope. All right, and these are really key pieces of information that we are going to need for today to talk about concave up and concave down. Now, if you remember from earlier this year, there is actually a point where we change concavity. All right, so if we were to look at this graph over here and just annotate for concavity, we can see that it starts with concave down. And one annotation I would make to myself, if this graph itself was, let's call this f of x, f double prime of x, let's see, what do I know about f double prime if it's concave down? That it's going to be negative. So we'll call that less than 0, right? We don't know what it is, but we know it's going to be negative during that whole time. Where over here it changes to concave up, I can see how that's shaped. So what do we know about the concavity over here with f double prime? F double prime is going to be positive, right? It's going to have to be a positive number, greater than 0, for concave up. All right, but we know that there is one point in the middle where that is dramatically different, right? And this is known as the inflection point. And this is where, if you remember, kind of an informal definition would be where concavity changes. So it could go from a concave up to concave down, or it could go from concave down to concave up. And another thing that we need to know, if concave down is always negative and concave up is always positive, f double prime of x is actually always going to be 0 whenever we change concavity. So both of these things have to be true in order for it to be an inflection point. Okay, So we need to kind of use all that information today. So if you need to kind of just unwrap that, take a moment, pause, go rewatch, and now join us on the example. Okay. So here's our example. We're going to take f of x equals this function, and what we're going to do is we're going to find all the intervals of concave up and concave down, and we're going to find all inflection points. Well, some annotations for meaning here that would help me understand to use the second derivative test. I see the words concave up and concave down. That tells me I must use the second derivative test, and it tells me something very specifically about the second derivative. Remember that for concave up, f double prime is going to be positive, and for concave down, f double prime is going to be negative. So if I can take the second derivatives and find if that's going to be positive or negative, I'll know concave up and concave down. And for inflection points, I know that f double prime has to be equal to 0, and I also know that f double prime has to change from positive to negative or negative to positive at that point. All right, so it's not a guarantee that it's an inflection point just because it's 0. I would also have to check that. So let's think about how we would actually do this problem. Well, the very first step here is we're going to take the first derivative. All right, before we can even take the second derivative, we have to take the first derivative. So we'll call that just f prime. And I'm going to very clearly mark that as f prime so that I know that. So just using the power rule, bring the 5 down, bring the 4 down, and 12x just becomes 12. Now for the second derivative test, step 2 is going to be the second derivative. I separated that into 2 parts just so that we didn't get ahead of ourselves. So I'm going to very clearly mark this f double prime, and I'm going to use the same exact rule, right? Power rule. 4 comes down, negative 120x to the third. The 3 comes down, 120x squared, and 12 is a constant, so that becomes 0. Okay. Now the third step is we are going to factor to solve. Okay, so if I were to factor this, and this is just like before, this is going to seem like a very similar process. We can actually factor out a GCF here, right? There's a 120 and 2 x's on each one of those. So I'm going to factor out a negative 120 and an x squared and just see what's going to be remaining. That means there would only be an x remaining there. And if I factor out a negative 120, I'll be left with a negative 1 there, but no x's. Okay, now when we factor to solve, we're going to set equal to 0, and I'm just going to put inflection with a question mark, right? We are actually going to be solving to see if this is going to be an inflection point. And remember that when we solve these, we just set those 2 parts equal to 0, and we solve from there. So if I think about this one, I would divide by 120, and then square root, well, that's still going to be 0. And if I add 1 to both sides over there, I get x equals 1. So these are possible inflection points. To be sure, we have to know if it's changing from negative to positive or positive to negative. So just like before, we're going to make our number line. So our number line in this case is going to include the points 0 and 1. And just like before, we're going to have to check some things and actually test some things out. So we know that at 0 and 1, it's going to be, well, it's going to be a possible inflection points, but we don't know the concavity in those regions. We don't know the values of positive, negative in here. So we're just going to check for concavity by plugging in to find our second derivative values. So anything less than 0 here would work, like negative 1. So we're going to find f double prime of negative 1 by plugging that in to our second derivative formula there. So I'm going to make this negative 120, negative 1 squared, and then negative 1 minus 1. And with this, I don't have to do all the math. Remember, we just need to know positive or negative for concavity. So this is going to be a negative 120. Negative 1 times negative 1 is a positive. Negative 1 minus 1 is negative 2. And we know that a negative times a negative, well, that's going to turn back into a positive. Now this actually tells me that it's going to be concave up during that part because the second derivative is positive. We don't know if this is an inflection point yet because it has to change concavity in order for that to be an inflection point. So we have to check between 0 and 1. I'm going to use 0.5. So let's find f double prime of 0.5. And that's going to be negative 120 times 0.5 squared. And then I'm going to have 0.5 minus 1. So I still have a negative 120. I still have a positive because a positive times a positive. And then remember that actually 0.5 minus 1, I'm taking away more than I have. 1 has a greater absolute value than 0.5, so that's going to stay negative. So if I multiply two negatives together, I still get a positive. So in this entire area, it goes from concave up, and it stays concave up. Well, that means that this cannot be an inflection point because it has to change concavity in order for it to be an inflection point. All right, but there's still one more region to check, and that's going to be above 1, so let's say 2. And we're actually going to find f double prime of 2 in the same way that we found the other f double primes. So doing this work here, I get a negative and a positive, and this time times a positive, which would give me a negative. Okay, and that's actually going to be concave down. So let's go back to what this question was asking us, which was to find all intervals of concave up and concave down. Okay, so concave up is when the second derivative is positive. So we'll say f of x is concave up, and we'll say on the interval, it's going from all the way to the left all the way until 1 is when it changes. So negative infinity all the way concave up, concave up, concave up to 1. And I'm going to say because f double prime of x is greater than 0, or I could say f double prime of x is positive on that interval. Okay. And then I could say f of x is concave down for where f double prime is negative, so that's going to be from 1 to infinity, because f double prime of x, and notice how I'm using f double prime of x, is negative, or I can say is less than 0 on that same interval. Okay, so that answers part A, where it says to define the intervals of concave up and concave down. The last thing is to identify all the inflection points, and remember that these two were potential inflection points because inflection points will have a second derivative of 0. But this is the only inflection point because it also has to change concavity. So I'm going to say inflection at x equals 1 because we'll say f double prime of x changes from positive to negative at x equals 1, and f double prime of 1 equals 0. So it satisfies both of those requirements for it to be an inflection point. That's the second derivative test. It's a lot of work. I'll see you in class. We'll get some practice done, and I'll answer any questions.